put the comment in parentheses before we get too far into this section. Delta H of reaction is the energy associated with the reaction, but sometimes they're specifically labeled. COMB stands for a combustion reaction. PREC stands for a precipitation reaction. So if you see some words you're not positive about, most likely they are the type of reaction, and you can still treat them as delta H of reactions. What does this all mean? It means that when we write delta H like this on the side of the reaction, we have a lot of extra information. First of all, we know that this reaction needs heat. We know that this reaction, the word is endothermic. We know that if someone wanted us to write the heat as part of the equation, because it's required, it's a reactant, and it would be like this, 153 kilojoules. Notice we've switched to kilojoules also. Earlier in the other section of the chapter, we weren't talking about kilojoules, we were doing all these reactions in joules. So enthalpies of reactions on the molar, 1 mole, 2 moles, mole scale, they're in the 150,000 joule range. So the tables in the charts don't want to constantly write numbers that large out. They just want to save space. And so they just put at the top of the column that the unit is a kilojoule per mole. And they put it like this. If you had to use this equation, this one isn't combined with the MCAC equation, but if you had to use a delta H value in an equation like in JINGHAM 2, you would need to definitely be aware as to whether or not the equation is expecting it to be in joules or kilojoules. And most of the time, you're going to have to convert it back to joules. Well, notice that this version of the reaction is the way it should be. It's the lowest molar ratio. So it just shows that you can't reduce this any further and everything is a whole number. So this is also a way to do more factor labels. You'll like this in a way because it's not new. We're just adding one more tool to your factor label toolbox. So in all of these cases, the energy is 153. What matters is looking at those coefficients. This is 153 kilojoules in 1 mole of zinc. Or if you flip it over, in 1 mole of zinc, there are 153 kilojoules. That's the conversion. If you're going to take a certain amount of grams of zinc and figure out how much energy in this reaction it will produce, or rather in this reaction, how much energy it will absorb. So this is 153 kilojoules in 2 moles because this right here is a 2. So in 2 moles of HCl, 153 kilojoules. Or in 153 kilojoules, there's 1 mole of zinc. Understood one there. Same here, zinc chloride. And then also our H2 is 1 mole and 1 mole. So you'll notice we basically can take the number that's over here and match it with any reactant or any product and turn energy and relate it to mass. Now let's do this first reaction. So write a possible thermochemical equation for 2 moles of sodium hydrogen carbonate. So the example's right there. So 2 NaHCO3 solid. And it says it's absorbing 130 kilojoules. You could put your heat on the left or the right of the reactants. So it's okay for me to put it there. And it's producing 1 mole of Na2CO3 solid and 1 mole of water. Water vapor is water as a gas. And 1 mole of CO2 gas. When you count these up, it should be balanced. Notice that if I were to write the delta H of the reaction, If I were to write the delta H of the reaction, I would write it over here as 130 kilojoules. So notice this is 130 kilojoules per 1 mole of CO2 per 1 mole of H2O per 1 mole of sodium carbonate per 2 moles of sodium hydrogen carbonate. So then let's see how many moles will be consumed if 75 kilojoules of heat were consumed in the reaction. And this is supposed to be a 65, if 65 kilojoules. So we take our 65, that's what we start with, and then we have this conversion factor. So because it's asking about the NaHCO3, I'm going to go over here and I'm going to say, oh, I have a coefficient of 2. With any time we have units, we need the kilojoules to cancel on the bottom, and now you know you can relate kilojoule to moles. And the reason we have a 2 in front is because our reaction had a 2 in front. When you do this math, and you might be able to do it in your head, you're going to get 1 mole of NaHCO3. And look, that's how many we produced, was one of these. So here's another example. Write the problem representing the energy within the reaction. Again, it's a combustion, and it says of 1 mole of CH4, combustion, and you might have wanted to know that that was a gas. That is a gas. Combustion always means reaction with oxygen, and it's telling you what it produces. And of course, it's over here to the side also. So that's going to be a gas, and that's going to be a gas. Remember, we said combustion is exothermic, and also this produces, that means we're writing the word heat as a product. And notice over here, this is how we would represent it off to the side. So pay careful attention. This throws people for a little bit. So I know it says that it's 890, but it's because it uses the word produce. Everyone knows that if you are producing heat, that means heat is going out. Now, how much heat is produced in joules? Notice in produce is produced. So we understand that it's heat going out. It's kind of a way of saying what quantity, or like what is the absolute value of heat. It's kind of like what it's saying. Just remember that that is heat out. So how much of that is produced in joules when 10 grams is completely consumed? So notice that 10 grams is not the same thing as 1 mole. So this is where we're going to change things up, and we will use that quantity, that 890, 10 grams. And again, we're getting rid of our grams, turning it into moles. And this number is from the periodic chart. We usually give it to you. And we're doing moles to moles. Notice we're not changing to another reactant or product, but we are converting to kilojoules because that is how much heat is produced. So it's like saying one of these is equal to that quantity of heat. Now it's asking in joules. So I need to take my kilojoules, change my kilojoules into joules. The reason that the answer is positive and not negative is because they phrased it saying how much heat is produced. The question is asking for the quantity of heat. The negative sign is understood with the use of the word produced. This much heat in joules is what's produced when all of those grams of CH4 are converted into energy. That's the theoretical yield of energy produced. Notice we started with grams. We turned into joules. And we used this number, and we used the in correlation with the coefficients to get there. The next problem, it's going to do the same thing in reverse. We're going to do joules to grams. And you want to look at how some of these problems are phrased so that you really understand it. So an unknown amount of methane was left in the pipes if this many joules of heat are produced when the methane is burnt. How many milligrams of CH4 is completely consumed? So look, you know up here, so these are both for the reaction up here. You know that a mole produces a negative 890-ish kilojoules. So you know this is going to be like way less than a mole. Make sure your answers that you're coming up with make sense. So we just take the joule amount that they give and we turn it into kilojoules because this number is in kilojoules. So we do joules into joules, kilojoules into kilojoules, moles into moles, and then we have grams into grams, and then notice we're left with milligrams. And that's only because they asked. Most of the time they'll stop at grams, but I just wanted to point out that sometimes you have to go further or less far when you're converting numbers. So these are the two ways in which you're going to be seeing the use of this number, this delta H number, with a reaction. You're going to be given a gram amount and asked to convert into a joule amount, or a joule amount and asked to convert to a gram amount. On your own work, question 3, all parts A through C, and question 4, parts A through C. Question 4C is the third style of problem you might get.